Okay, guys, this question asks you to calculate the frequency of a photon that gets emitted from the transition of an electron in a hydrogen atom when the electron moves from a quantum level equal to 5 to a quantum level equal to 2. So you're going to use the Rydberg formula, and the Rydberg formula helps you get understanding or get your head around what's going on in energetic transitions of electrons and hydrogen atoms. The Rydberg formula can be presented to you in many different ways in terms of energy, in terms of frequency, in terms of wavelength. They're just all algebraic manipulations of each other. So usually I present the formula in terms of wavelength. You need to know that the photon is emitted. So this implies that the electron lost energy. If the photon is absorbed, then the electron gains energy. And so if the photon is emitted, then the electron loses energy. So the quantum level starts off at high and ends up being lower. And so that's something that you need to know. However, the Rydberg formula is always presented to you in the same way. As far as I'm concerned, 1 over the wavelength equals the Rydberg constant times 1 over n squared subscript L minus 1 over n squared subscript H. And those two subscripts mean higher quantum number and lower quantum number for H and L specifically. The higher quantum number must always be in that term 1 over n squared H, the one that's on the right. If you don't have it that way, then things end up being negative and they get confusing. And so this will help keep everything straight for you as you go along. So the rest is just really an algebraic manipulation. You have to look up the Rydberg constant, 1.097 times 10 to the 7th per meter. Notice that's not 10 to the 7th meters. It's 1.097 times 10 to the 7th per meter. And so we get 1 over 2 squared minus 1 over 5 squared. And rewriting that, then I would say 1.097 times 10 to the 7th per meter over 1/4 minus 1/25. If you take the 1/4 and you subtract from it 1/25, you get 0.21. So we end up with 1.097 times 10 to the 7th per meter times 0.21. And what we get from that is 2.303 times 10 to the 6th per meter. Now, what we need to do here is that ultimately we want the wavelength, and this is giving you the inverse wavelength. And so in order to get the wavelength, we need to take the inverse of both sides. If we take the inverse of both sides, we get the wavelength on the left, and on the right, we get 4.3416 times 10 to the negative 7th. And if you take the inverse of per meter, you get meters. Okay, now that you have the wavelength, you can go back to another formula. So this is sort of two formulas in a row. Frequency equals C over lambda, and you can use this to calculate the frequency. So 3 significant figures for the speed of light, 3.00 times 10 to the 8th meters per second. Let's take our calculated wavelength, 4.3416 times 10 to the negative 7th meter. We'll do the calculation, and we get 6.91 times 10 to the 14th per second, which is a hertz. And that'll be the final answer. Okay, thanks.